So the other day, we were talking about metals. Metals tend to become cations. What kind of charge do cations have?
Negative.
Positive. Okay. Cations are positive. This one I just want to highlight, though. So pay attention, focus. We will do some practice problems later. If it's a cation, the name doesn't change. Okay, so sodium is just sodium. Okay, if it's neutral or if it's Na+, we still call it sodium. Okay, so name doesn't change for cations. Then we talked about nonmetals the other day. And did we actually talk about anions in the naming?
Yeah.
Okay, anions have what kind of a charge? Okay, negative. Anions do get a different name though. Okay, so you still keep the root word of the name. However, you drop the ending and you add "ide." So for example, sulfur is going to become sulfide. Okay, chlorine becomes chloride. What do you think fluorine becomes? Fluoride. What does oxygen become? Oxide. Good. Okay, and with more practice, you'll get way more comfortable with those names as well. Okay, when we also talk about like names and formulas, some of our elements exist as diatomics. What does di mean? Two. Di. Di means two. Okay, and atomic is atoms. Okay, so some of our elements exist in pairs. Okay, so they're just two atoms bonded together. You need to know these. And so these 7 are bromine. So like physics-wise, bromine isn't stable as a single atom. So when it's by itself, like not bonded to any other elements, bromine is always bonded to itself. So we write Br2. Okay. Iodine is another one. So instead of just plain old I, we always write the formula I2. Okay. Nitrogen, whenever it's alone, it's just N2. Okay. Chlorine is Cl2. Hydrogen is H2, oxygen is O2, and fluorine is F2. Okay. The key is diatomics only exist when these aren't bonded to anything else. So I'm going to use oxygen as an example. Okay. So first of all, how many of you have seen oxygen written as O2 before? Okay. Good. That's because there's no such thing as just oxygen by itself. It's not stable. So oxygen bonds to other oxygens. Okay. However, when it bonds to a different element, it doesn't stay O2. And another common example is water. What's the formula for water? Okay, H2O. Notice how once it bonds to other thing, it's no longer O2 automatically. Okay, so these only exist when they're by themselves. Yes. Okay, so you have to know these 7 elements. So I have 2 ways for you to remember them. The first one is remember the word Brinkelhoff. Everyone say Brinkelhoff. Okay, Brinkelhoff. I purposely put them in this order, okay? Do you see how if you read them in this order, it spells out Brinkelhoff? Yeah. Okay, so if you can remember Brinkelhoff, you can remember the BR, okay? So INCLHOF. Okay, so Brinkelhoff, say it again. Okay, Brinkelhoff. Those are our elements that exist as pairs. Also, how many are there? Count. What's the number up there? There's 7. Okay. If you look at them on the periodic table, they almost perfectly make a figure 7. Okay. So do you see how if you like color them on the periodic table, they make a 7, except you would just have to remember a little hydrogen on the left then. Okay. So use one of those tools to help you. So you can remember it's the 7 in like the upper right-hand corner plus hydrogen. Okay. Or you can remember Brinkelhoff. Okay. You pick one. Yeah. 7s or Brinkelhoff. Okay. If you remember both, even better. Okay, but it's just starting in this unit, we start writing formulas. So now's just a good time I want to introduce these 7 have special formulas because they're diatomics. Okay. All right, you with me? Okay. Okay, so last class we did a lab, and the whole purpose of the lab was to figure out properties for ionic compounds and covalent compounds. Okay. That's something that we have to do first before we can name, because it turns out ionic compounds follow like one set of naming rules, and then covalent follow a different set of naming rules. So we have to figure out how to identify compounds as covalent or ionic. So covalent compounds are typically made up of nonmetals. And if y'all look at the slides, can you see not every word is bolded, but can you tell like nonmetals is bolded? Okay, so make sure you get those bolded words down. So covalent compounds are made up of your nonmetals. Okay, so a nonmetal bonds to a nonmetal. So for example, we have like H2O, which is water. Okay, so we look at H2O. How can we tell the different elements in a formula? Okay, by the capital letters. So you just look at each capital letter, and we look at if the elements are metals or nonmetals. So let me show you like a little trick. Everyone take out, you probably grabbed a new periodic table today, right? It had the naming chart on the back. Okay, take a look at the periodic table. Okay. It also matches the one up here on the wall. Do you all see, you have like a bolded line. Over here it's blue. Do you see on yours you still have like a bolded line? It matches where this is. It might be kind of faint. Okay, if you need to shade it in. Do you see this like bolded staircase over here? It's blue. Okay, yours is also bolded. The copying is a little light, so if you want, you can shade it on this periodic table. So I call it the bolded staircase. Okay, so what that bolded staircase does, it takes the metalloids that we talked about last class, and it's basically dividing them in two. Okay, so if we wanted to live in like a black and white world, you would take the bolded staircase, everything to the left, you're going to consider a metal. Everything to the right, you're going to consider a nonmetal, except there's one exception. What's the one exception? Hydrogen. Okay, hydrogen's to the left of that line. However, hydrogen is not a metal. Okay. So whenever you're taking like a test or anything, you will always get the periodic table with the bolded line. So you don't have to memorize like element name. But you do need to know everything to the left of that bolded line, we're going to consider a metal. Everything to the right is a nonmetal. Everything to the left of the bolded staircase, you're going to consider a metal. Everything to the right, you're going to consider a nonmetal, except hydrogen. It's on the top left. It is a nonmetal. Okay, so then to figure out if something is molecular or covalent, you're going to use this. So if we use water for an example, you know each individual element because you're looking up capital letters. So H is hydrogen. Is that a metal or a nonmetal? Okay, nonmetal. What's oxygen? Okay, so when they're both nonmetals, you're thinking covalent. Okay. Another example is carbon dioxide. So you look at the C. Is carbon a metal or a nonmetal? Okay, nonmetal. And oxygen, nonmetal. Okay, so you should be thinking nonmetal plus nonmetal is a covalent compound. Or molecular, are these two the same thing? Okay, same thing. I tend to say covalent more, but you need to recognize molecular and covalent are the same compounds. Okay. These ones have the properties of that low melting point and the low boiling point, so that's why you saw them melt in our lab. Okay. And then typically they're a gas or a liquid at room temp, and that's because they have that low boiling point, okay, and the low melting point. So usually gases are liquids, right? So think water. What's water at room temp? Liquid. And what's carbon dioxide? Okay, gas. So typically, there are exceptions out there, like the 3 we used in our lab, but for the most part, gases are liquids. Next, we have ionic compounds. What word do you see in ionic? Ions, okay? So ionic compounds are when ions join together, and specifically it's when a cation bonds to an anion. Okay. What kind of charge does a cation have? Positive. Think T and cation. Think T is like positive. Okay, so think like T. Do you see how it kind of looks like a plus symbol? Or who's a cat lover in here? cat lovers think like cats are positively awesome or something. Okay, what charge do anions get? Okay, what do opposite charges do? They attract. So ionic compounds is always a cation and always an anion because those opposite charges are going to attract and cause them to bond together. Okay. When we're looking at them on paper, we're typically going to see a metal and a non-metal bonding. Okay. There are a couple exceptions to this rule, but for the most part, it's going to be a metal bonded to a non-metal. Okay. So if we're looking at the periodic table, how are you going to know if something's a metal? Good. You're looking at that bolded staircase, and what side of the staircase are the metals? Left. Okay. So if it's on the left, it's a metal. Where are the non-metals? Correct. Okay. So you're going to have to use the periodic table to know if you have a metal bonded to a non-metal. All right. So ionic compounds form when ions bond. However, they're electrically neutral. Okay. And think a very popular one is sodium chloride, which is table salt. When you touch your table salt, does it shock you? Sure. No, right? It's neutral. There's no charge on your sodium chloride. So ionic compounds are neutral. So that means however many positive charges the cation has, there has to be an equal but opposite charge coming from the anion. Okay. So the positive charges have to balance out the negative charges. Okay. So overall, ionic compounds are neutral. And then most of them end up being solids at room temperature. Okay, so think like table salt. In our lab the other day, we also use like calcium chloride. Okay. I think we use potassium iodide. What kind of salt do you throw on the ground when it's icy? Good. Mag chloride, magnesium chloride. Okay, so think like salts are good examples of ionic compounds. Okay. You don't need to write anything down for this slide. Where we're going to go next is we're just going to look at chemical formulas, and we're going to identify them as ionic or covalent. Okay. Don't write this down. Chemical formulas, they just show you like what elements are present and then the quantities. Okay. Okay, so here I give you some formulas. All we're trying to do is just classify them as ionic or molecular / covalent. Okay. So the first one is KCl. What are we looking for to distinguish the different elements? What do you think? Okay, capital letters. Every time you see a capital letter, it's a new element. So our first element is K, okay, which is potassium. You're going to look at your periodic table. Is potassium a metal or a non-metal? Okay, it's a metal. And then Cl is chlorine. Is that a metal or a non-metal? Okay, so if it's a metal bonded to a non-metal, what kind of compound is it? Okay, I'm just going to put I for ionic. Next, we have CO, which is carbon monoxide. So C is carbon. Is it a metal or a non-metal? Okay, non-metal. What about oxygen? Okay, so how would you identify that? Okay, you call it covalent or molecular, whichever. You can pick a letter, doesn't matter. Okay, let's do one more together. SR, Se. SR is strontium. That's a metal. Okay, it's a metal. Se is selenium. Non-metal, so how would you identify it? Okay, good. Ionic. Okay, I want you to try the next 5. Try them. Is it okay if you get them wrong? Yeah, but I want you to try. So get out your paper. I want you to write I's or C's or N's next to it. Okay, how did you classify BaO? Okay, ionic. Barium is the metal. Oxygen's a non-metal. What about CaCl2? Okay, ionic. Calcium is the metal. Chlorine's the non-metal. What about SO3? Okay, this one should be covalent. You could call it molecular. Sulfur is a non-metal. Oxygen's a non-metal. How did you classify CCl4? Okay. It should also be covalent or molecular. Carbon's a nonmetal. Chlorine's a nonmetal. And then finally, what about MgF2? Okay. Ionic, magnesium's the metal, fluorine's the nonmetal. Have you noticed a pattern? What patterns have you noticed? What pattern have you noticed? Okay, if there's a metal, it's always first. What is the second element no matter what? Okay, have you noticed that the second element on all of these is always a nonmetal? Okay, so if you're trying to decide if it's ionic or covalent, which element do you really need to look at? First one. Okay, so if it's a metal, what do you know right away? It'll be ionic. If it's a nonmetal, what do you know? Covalent. Okay, good. Do you think you could do some of those on your own? No. Yes, no. We're going to practice. Okay, before we practice though, I want to move on and talk a little bit about metals and charges metals get. So we need to talk about something called oxidation numbers. Before we just like mindlessly copy down oxidation numbers, I want you to think back to maybe like a week and a half ago, we did that little ion simulation on your iPads. Do you remember that? Okay, why did atoms become ions? What was the whole point of adding or gaining electrons? If you need a hint, you can look up here.
Yeah, that's what I was going to say, is to satisfy the want for the electrons to be like full.
Good. Okay, so atoms become ions because they're trying to satisfy like a filled valence shell or a filled outer shell. How many electrons do atoms want in their outer shell? 8. Okay, so they're either going to gain electrons or lose electrons to get to 8. So, some of the elements are super easy to predict. Like some of the elements we know how many electrons they're going to gain or lose to get to 8. Let's just use oxygen as an example. Oxygen has 6 valence electrons. How many does it want to have though? 8. So is it easier for oxygen to gain 2 or lose 6? Gain 2. Okay, so oxygen will always gain 2 electrons to get that filled shell. If it gains 2 electrons, what kind of charge does it get? Negative 2. Okay. So for some of our elements, we know how many electrons they're going to gain or lose to get to 8. That is called an oxidation number. Okay. So go ahead and write down what an oxidation number is. Okay. So it's just a number. It tells us how many electrons that element is going to lose or to gain to get to that filled valence shell. Okay, so some of those elements are very predictable, like oxygen. So we're going to label the predictable ones. Go ahead and pull out the blank periodic tables that we've been coloring on.
Is it color time?
Not color time, it's label time.
That's boring.
It doesn't have to be. I would get a blank one. Get those out. Okay, so some of the columns of the periodic table have very predictable oxidation numbers, so those we're going to label. Okay. Find the periodic table. Do you remember one of them we labeled columns with like numbers and letters like 1A, 2A, 3A, and so on? Okay, get that one out. Okay, so the ones that's 1A. Elements in column 1A, which is the very first column. Okay, so it's the ones like lithium and sodium in it. Those have an oxidation number of +1. We write it in the format, though, of number first, symbol second. Okay, so these have an oxidation number. You can say +1 or 1+.
I'm very confused. Do you want us to just write it underneath it, like underneath the row?
Underneath, on top, doesn't matter. But you need to know column 1, the very first column of the periodic table. Those elements get a +1 oxidation number. Okay. Yep. The very first one, very first column, +1. Okay. The second column, okay, the column that you labeled 2A, This is literally the second column on the periodic table, right? Beryllium is at the top of it. These ones get an oxidation number of 2+. Okay, then we're going to jump to 3A. However, 3A is like you skip the whole transition metals. So we're jumping all the way over to that right side. The one that aluminum's in, boron's at the top. Okay. So where aluminum is, these get a charge of 3+.
Does it just increase by 1?
Nope.
So that's probably like 4.
Nope. Okay, the next column over,
That's 0.
you've labeled it as 4A. It doesn't get one. Next chapter we'll talk about electrons, but elements in this column, they don't want to gain or lose electrons. We'll talk why next chapter, but it has to do with stability. Okay. So then you go over another column to 5A. This is the one where nitrogen is the very first element in the column. These ones have an oxidation number of 3 negative. Okay, they would rather gain 3 than lose 5. Okay. Then we move over just another column. So you labeled it 6A. Oxygen is the top of this column. Okay. These have an oxidation number of 2 with a negative charge. And then finally, on the column you labeled 7A, it's the one that has fluorine at the very top of it. These ones have the oxidation number of -1. Okay. And then the final, like the very last column of the periodic table, they don't get charges. They have filled shells. So if they already have a filled shell, are they going to want to gain or lose electrons? So they won't get a charge ever. Okay. So those columns that you just labeled, those are our predictable columns. Okay. So for today, for tomorrow, for Friday, use this to help you remember that like everything in this column is +1, +2, +3, -3, 2, 1. However, you need to get to the point where you just have those columns memorized. Okay. Is it okay to like use your cheat sheet for a couple days?
Yeah.
Yes. But eventually, you need to get to the point where you just know column 1, they get a plus charge. Column 2, they get a +2 charge. Column 3, which is where aluminum is, get a +3. Okay. And then our fifth column, -3, -2, -1. Okay. All right. Now, if you look at the periodic table and what you just labeled, are we missing a big chunk?
I know.
Okay. What's the name of the big chunk that we just skipped over? Okay, transition metals. Transition metals don't fit like this really nice one-size-fits-all rule. So transition metals, they can have more than one ionic charge. Okay, which means there's not a one-size-fits-all rule. They're a little bit more complicated. Okay. In addition to transition metals, tin and lead also follow this rule. They're not transition metals, but they follow this rule. Okay, so since transition metals don't follow the predictable oxidation number pattern, we have to state the charge in the name. Okay, since they can have different charges, you just have to put the charge in the name. So when we name transition metals, we use the current system, which is called the stock system. So I'm going to start, this is the system we use, so this is the system you need to know. The stock system is just the name of the metal with the charge in Roman numerals. Okay, so it's just name, charge. That's how we know what we're talking about. So then I just have some examples below. What metal is Fe? Iron. Okay, so iron can sometimes have a +2 charge. Other times it can have a +3 charge. That changes depending on what iron bonds to. Okay, so then since the charge changes, you have to put that in the name. So iron, if we're doing symbol, you can write Fe with a 2 in Roman numerals in parentheses. Or you can spell out the name, just iron, with a 2 in Roman numerals in parentheses. Okay. And then if you were just going to read it, you would say Fe2 or iron 2. So that's just how we communicate the charge of that. Iron also has a 3 positive charge sometimes, so you write Fe with a 3 in Roman numerals in parentheses, or iron with the Roman numeral 3 in parentheses. And again, you would just say it as iron 3 or Fe3. Okay, I want to show you the classical naming system. You don't need to know this system, but sometimes these words pop up, so I just want to show you like where they come from. Okay, the classical naming system is when you take the root word that's usually Greek, sometimes Latin, and then the ending changes to us or ick depending on the charge. So iron symbol is Fe. Have you ever wondered where Fe comes from? Well, it comes from the Greek root. So it's either ferrous for the lower charged cation or ferric for the higher charged cation. Okay. We don't use this one anymore because the stock system is easier. However, some of the chemicals, like if you ever read the containers, some of them are just old or some of them still will follow classical. Okay. So just if you ever see ferrous or ferric, it's just telling you what the charge is of that metal. Okay, we're going to practice. We're just going to name these 4 transitional metals using the stock system. Okay. I'm going to help you with the first one. So the first one is Mn with a +2 charge. On your periodic table, find Mn. What is the name of Mn? Don't get it confused with Mg. Okay, so Mn is manganese. Okay, and what's the charge of manganese? 2. How do you write that? Okay, so just Roman numeral 2 and then put it in parentheses. So it just looks like manganese 2. Okay, you try the next 3 on your paper. What is Pb? Okay, lead, and the +4 is just telling you 4. So Roman numeral 4 is just like IV. Okay, so lead 4. What is Sn? Sn is tin, so the first one is just tin 4. Second one is tin 2. Okay. Are just these groups of atoms that are called polyatomic ions. I don't think you need to write the definition because the name kind of spells it out for you. What does poly mean? Okay, poly means many. What word do you see as an atomic? How about atoms? So polyatomic ions, they're just many atoms grouped together. And what does an ion mean? They have a charge. Okay, so polyatomic ions, they're these like tightly bound groups of atoms that they behave as a single unit and they carry an overall charge. So if you need to write down the definition, you can. However, now that we like break apart the name polyatomic ion, does it say the exact same thing in the name? Okay, so if you're good with the name, then that's all you need to write down. So polyatomic ions are extremely popular. They show up all the time, and we just have to get familiar with them and we have to know how to use them. So if you grabbed a periodic table today, look at the back side. So the back side is a list of what I would call the most common polyatomic ions that we use in high school chemistry. Now if you get on the internet and you Google more, there are a lot more out there. Okay, these are just the most popular ones. So these are the polyatomic ions that we use. Okay, so you don't have to memorize them. You always get to use this chart. Okay, so we just have to know how to use the chart. So everyone take a look at your chart. If you didn't grab one at the beginning of class, where would you find them? Okay, over there. So this one is yours. You can write on this one. When we get to test days, I just give you like a blank like this, but like you can't like put notes on it. Okay, that's all you need. This is what you need. Okay, look at the left side. Left side are all of your positive ions. Okay, so your cations are on the left. Also, if you look at the column, they're alphabetically arranged. Okay, so just kind of help you find things better, they go alphabetical. The right side are all of your negative ions. Also, it goes alphabetical. Okay, so that should help you be able to like sort through it. Some of these words are very, very, very similar, but they're different. So look at kind of in the middle. Find nitrate and nitrite. It's like in the middle of your page. Second column. They're also here. Okay. Hold that thought for just a minute. Okay. Have you all found nitrate or nitrite? Have you found those on yours? Okay, I just want to point out that some of the names are very, very similar. So like nitrate is NO3 with the 1 charge. Nitrite is NO2 with the 1 charge. So if you're using the polyatomic ion chart and you're looking for nitrate, but you find nitrite, don't just be like, good enough, I'm going to use it. Okay, so I want to point out, there are very subtle differences in the polyatomic ions. There are patterns of like knowing when you use atonite. We don't have to memorize those patterns though, okay? If you look, there's also sulfate, sulfite. Those are very similar. You have chlorate and chlorite. Okay, so just be aware that making sure you're finding the correct name or formula. Yes?